Sometimes when we have measurements, we want to use these to predict future values. For example, if we're given measurements x and y, so data points x and y, and then in the future we want to be able to measure x and predict a value for y, we can use regression to do this. And regression depends on the order that we approximate the data with. So here is a 0th order approximate. We're saying that we're predicting y to be c, which is a constant value. If we use least squares approximation, which we'll get into in a little bit, then we come up with a value for c that's just equal to the mean. So least squares tells us that the best value for y would be the arithmetic mean. We could also use a first order approximate. We can really use any order approximate that we want, but we'll look at first and second order approximates, well, and higher orders too. But for right now, first order approximate shows that y is ax plus b. So given these data points, we would pick a line to predict future values of y. If we measure an x value, then that would give us a value for y. And we want this to minimize the error. So we want this to be the best fit possible. And we need to define what we mean by best. So here is a value x1, y1, and then the predicted value at ax1 plus b. And the error is the difference between the measured value and the predicted value shown here. We can generalize this for all the I points, and then that leads us to a value for our cost function, which is what we want to minimize. This S sub r is known as the regression sum of the squares. Well, not quite yet. So we just have here, this is the, anyway, let me back up. This is what we'll try to minimize, this S sub r. And I'll get into that in a second, why it's called S sub r. But we want that to be as small as possible. And that's how we'll say that it's the best. So right now we have S defined as the error, the difference between, well, actually the sum of the errors. So it's for every data point I, it's the difference between the measured value yi and the predicted value yi. And then we add all those together, and that gives us SR, which we want to minimize. And then we'll say we found the best fit. One problem with this formulation for our cost function is that we could just raise this line, raise the predicted values, and then all of our errors would be negative. So we would come up with a smaller and smaller value the more negative they were. And here's the same thing for the 0th order approximate. Well, here we have the regression cost function or error, and here we have the total. So this is the difference between every measured value and the mean. So instead of just using the error, we could use the absolute value of the error, and then we would no longer have the issue of being able to make them more and more negative. So we wouldn't have negative values for our cost function. But for reasons that we won't get into now, it's preferred to use the squared error. And then we don't have negative values, but it has some advantages over using absolute value. Now here we have the sum of the residual squares, and that's the cost function that we want to minimize. And this is the sum of the total squares. This is called S sub t. But S sub r is what we want to minimize in order to deem a fit to be the best fit. Correlation coefficient is r, and it's given by this equation, 1 minus the regression sum of the squares over the total sum of the squares. 1 means it's a perfect fit, means that our regression fits the data perfectly, and 0 means that it's a useless fit. We will get into in a minute how to come up with the values for the coefficients for our regression, but for now let's look at the correlation coefficient in more detail. We also have here the standard deviation. Well, if we square this, this would be the variance and the covariance. So this is the correlation coefficient, where we're using sigma yx squared, and you can see that it differs from using the regression sum of the squares whenever n is small. So we'll have this value, this ratio here that's different from 1, and so we come up with a different value. And so this is what we use for the correlation coefficient in -2. In order to get the coefficients for our fit, we want to minimize the error. And the way we'll minimize that is to differentiate our cost function, minimize the cost function. So we'll differentiate the cost function with respect to our coefficients. So the partial derivative of S sub r with respect to b, and the partial derivative of the cost function with respect to a. Set those equal to 0, and we will find the minimum value for our cost function as the coefficients change. Solving those equations, we get these values for a and b, and they're just dependent on the measurement, the data points that we have. So you can see a and b are dependent on sums that come from the data points. As I said earlier, we can perform regression for higher order functions. Say this is our data. You can see that 0th order regression doesn't fit it very well. First order regression doesn't fit it very well. So we could use a quadratic approximate to get a better fit. Or if we know that we expect this value to follow a quadratic, then we can go ahead and use a quadratic regression. So here's the regression. We have a second order approximate, and we use the same technique in order to come up with these coefficients a0, a1, and a2. Our cost function is, again, the difference between the measured value and the predicted value squared, and then sum all those differences. So we follow the same path as before, where we take the partial derivative of our cost function with respect to the coefficients and set those derivatives equal to 0. In this case, we come up with a system of 3 simultaneous equations and 3 unknowns, and we can solve for those unknowns to get the coefficients to our quadratic function. This is that system again, and here it is in matrix form. So you can see that we can just solve for a0, a1, and a2, given our data points. We can perform a regression for any order of polynomial that we want. Here's an example where we have a 5th order regression. Our data comes from this function, and we want to fit a 5th order curve to that function. So here's MATLAB code for doing that. We come up with our data points x and y. So these are 2 vectors, and we can just use the polyfit function with these arguments to get a 5th order approximate or regression for that data. Up till now, we've had one independent variable, which has been x, and one dependent variable, which is y. We're doing a fit in order to predict y based on x. So here, for first order, we would come up with this fit, and then if we made measurements of x, we would be able to fit a value for y. But there are some cases where we have more than one measurement, more than one independent variable. And for that, we perform multivariate regression. So in this case, we have our result y is equal to b plus, this would be a first order multivariate regression, m1 times x1 plus m2 times x2, all the way up to our m independent variables. And our cost function, this should be squared, but our cost function is the difference between our measured value and our predicted value. So this is for all the data points, and then this summation is for all the independent variables. But whether or not we have one independent variable or m independent variables, the process is the same for finding the coefficients. We take the derivatives, the partial derivatives of our cost function, set them equal to 0. And here is what the regression would look like for this system where we have 2 independent variables. Our result is given by this function. And if we wanted to fit that to a first order approximate, then we would come up with this function here. So the coefficients would lead to this plane.